In this part, we do a review of Verilog constructs, some of what we have already seen. I'm just putting everything in one place and then covering some of what you have been doing wrong in your homeworks or some of the gray areas that you have. I'm trying to cover in this lecture in Verilog. So let's start with combinational Verilog constructs. This is not necessarily combinational for combinational circuits, but since we are summarizing our Verilog knowledge at this point and we have only covered combinational circuits, we are saying combinational Verilog constructs. Let's start with the famous easy numbers. As if we have seen numbers, for example, 25. You have no problem in Verilog to say assign something a equal to 25, okay? And if you just say 25, it is assumed decimal, okay? The default is decimal. But then if you do that, it takes 25, turns it into a 32-bit number, and then it looks at A, and if A is like 4 bits, it only takes the rightmost 4 bits. If A is 16 bits, it truncates the 32-bit 25 and then just drops the rest of it. That's doable, that's okay, but then it would be best if you always specify the size you want. For example, A is a 6-bit number, and then you say A equal 6 single quote. Okay, so this means A is 6 bits. And then you have to specify the base of the number. So maybe you say it is binary and then give it 011001. This is 6-bit. And if you give it more, it just takes 6 bits. If you give it less, it puts zeros on the left-hand side. Okay, that's if the numbers are unsigned. And for now, we are only talking about unsigned. Or if the number is, for example, you can say 6 tick decimal 25. It means 6 bits, but then decimal 25. Decimal 25 turns out to be this. Okay. 1, 2, 4, 8, 16, so it's 25. And this is 5 bits, so it's going to put the 0 on the left-hand side. Turns out to be the same as what I had up there. And A becomes 6 bits like this. Or you can say A equal 6 bits hex 5A. 5 is, well, 0, 1, 0, 1. A is 1, 0, 1, 0. But then you said 6 bits, so it's going to take 6 bits and 6 bits. And then A becomes this. Okay? This is numbering. And sometimes you may want to repeat a number and a certain bit. You can say, I like to repeat 6 times curly bracket 3 tick B101. This gives you 101, 101, 101, 101, 101, 1, 2, 3, 4, 5, 6 times. Okay? And these are curly brackets. These are replication operator, which we also use for concatenation. So that's all I want to say about numbers. We have seen numbers, and a lot of time it looks easier to just say 25, or when you're checking numbers, you say if something is equal, if select is equal to let's say 0 or select equal to 1 or something. Actually, if you don't put the size and the base of the number, again, it starts with decimal and then turns it into 32-bit and then 32 bits and then looks at the left-hand side and adjusts the size accordingly, truncates. And if this left-hand side is more than 32 bits, it will put zeros on the left-hand side for unsigned numbers. All right, so that's with numbers. And then let's do transistors. This is a PMOS transistor. And the way it's written in Verilog is PMOS. Okay, sharp sign. Okay, the sharp sign here is for the delay. PMOS can take 3 delays, 5, 6, 7. Or maybe you don't want 3 delays. Maybe you only want 1 delay. So you say PMOS only 5. Okay, or maybe you want the average of the 3, you put 6. And then you have a transistor name. For example, this is transistor T1. And then you put the connection to the ports. The first port is the output. So if this is connected to this output W, this is W. The next port is the input, which if it is PMOS, the input for a PMOS comes from supply. Always PMOS connect to supply, NMOS connect to ground. And then you have the, let's say I name this as VDD, and therefore you say VDD. And then let's say this is your A input, and this is your A input. Okay, so this is PMOS. This is called primitive instantiation, meaning that you are instantiating the PMOS. You are instantiating PMOS, which is a primitive of Verilog. That means Verilog knows it. It's not a module. It's just a primitive that Verilog knows it. And then the arrangement of the inputs and outputs are exactly as Verilog decides. Okay. Gates are also primitives. All right. So let's put another NMOS here. Sharp sign. Usually NMOS is faster than PMOS. So let's say if that one, the average is 6. I'm going to put 4 here. This is my transistor 2. By the way, the transistor name or transistor identifier or the instance name for the primitives is optional. Okay. This is an NMOS, and then the output comes first. The input comes next. The NMOS come from ground up, and I'm trying to build an inverter, and A becomes this. All right, and then this is your ground, and then G and D. And in order to build the circuit, I say supply 1 VDD, supply 0 G and D. Okay. So that's this circuit here, but then you want to put this inside the module. Let's talk about module. Module begins with the keyword module, and then you put the name of the module. I like to call this my inverter. And then the inputs, however you want. You want to put the output, you want to put the output, whatever you put here. That becomes the order of this inverter. The order of the ports of this inverter. So if you say input, whatever you want to call it, AA maybe, and output A invert, okay. Then you say end module, and then whatever is this goes here. Now you have an inverter. Something about the use of NMOS and PMOS transistors. NMOS is always the structure. You don't mix them. Okay. You have the output. On top of the output in the direction of supply, those are only PMOS transistors. Below the output, those are NMOS transistors that connect to the ground. You cannot switch them. You cannot put NMOS on top and then PMOS at the bottom. That's because of the transistor property. Okay, physical property which we are not talking about here. That's why, because you always put NMOS on the ground side and PMOS on the supply side, all the complex gate structures you develop, they are all inverted. Like this one is a simple inverter. Okay, if you put two transistors in series and two in parallel on the top, then that becomes a NAND gate, and that is a NAND gate. So again, it is inverted. Okay, with CMOS structures, you cannot build AND gates and OR gates. All right, so that was Verilog from this point of view. But then you can have gates. Okay, you can have gates. You can use primitive gates, or you can use your own gates. Okay, for example, I can build my module, my NAND, and then input. AA is in the input, BB is an input, and then NAND output, let's say NAO, is W. You have to say out. NAO. Okay. Output. All right. And then here you can put 4 transistors, which follows the same format you had before. So here is my NAND gate. Okay, this is my NAND gate. This is my module. But then Verilog also gives you primitive NAND, primitive AND, primitive OR, primitive XOR. Primitives are built in Verilog, and you don't decide on the order of the inputs and outputs. Like, for example, NAND. Okay. And I can always use an AND. I can always use a NAND and primitive NAND in my design, but then I have to follow the rules of Verilog for the inputs and outputs. The way it works is this. Once again, you can put up to 2 delay values, and then the gate number G1 or the instance name is optional, and then, like I say, G1 for example, and then the outputs come first. The output comes first. So if you want to connect W to the output, and then you have 3 inputs or 4 inputs, this is how you do it. Here is a 3-input NAND gate, A, B, C, instantiated from the Verilog primitives. Oh, let's do this. Let's take this NAND gate and put this next to a NOR gate, and then let's build this circuit. Okay, let's build this circuit. Okay, so this is what I'm going to do. I'm going to write this module, some circuit, input A, B, C, D, output W, and here let's get an instance of NAND. NAND is a primitive, and NAND is a primitive, and the delay is, let's say, 5 nanoseconds. The output is a wire here. Let's call this one Y, and therefore I need a wire Y. Okay, and then the Y is the output. A, B, C are the inputs. Let me be a little bit more clear here. Wire Y, and then NAND, sharp sign, 3,5, and then the gate number G1, for example. So I'm calling this one G1. the output is Y, the inputs are A, B, C. And then I have a NOR. NOR is also a primitive, sharp sign. Let's say this is 2 inputs, so the delays are a little bit less. This is G2, the output is W, the inputs are Y and D. Okay, I just built this circuit. Now let's say that I build my own NAND. If I build my own NAND and my own NOR, okay, like for example, this is my NAND. Sorry, module. My NAND. And then I have decided that the inputs are AA, BB. It's only a 2 input circuit. And the output is NAND NGO, NAND gate output. I don't remember what I did before, but then here is end module. Okay, you can describe this however you want. You can put a primitive there if you want, or you can put transistors there, or you can put whatever. Let's say I have this, and then I also have another module, and this one is my NOR. And then again, that one has AA, BB, and NGO. I don't have a problem if I call them both the same because they're in separate modules. And then you are describing both of them here. All right, so what I want to do is, in blue, I want to build this circuit, A, B, C, and then this W. Okay, so I come up with a new module, call it module. This is some circuit. How about some other circuit? Some other circuit. Okay, the inputs are A, B, C. Output is W. And now I have to instantiate my module. This is not primitive anymore, it is a module. So I instantiate my NAND, and therefore I say my NAND instead of NAND. Now here, first of all, I cannot give delay. If I have delay, fine. If I don't have delay, I cannot specify. Secondly, the module name is, the instance name is mandatory. So module 1, and then third, so 3 differences. One is timing only works if you already have the timing in your NAND, which I don't in this case. Not in the ports, not in the parameters. Secondly, the name of the module or the instance name is mandatory. Third, the input outputs are not set as they are set in the primitives. These are primitives. The inputs and output order is set the way you have described it, and therefore what I want to say is I want to add I want to connect A to the first port of my NAND, so I put A here. B to the second port of it. To the third port, I have to declare this. Let's say I declare it Y, and therefore there is a wire Y here. Okay, the third port, which is the output, I declared it as Y, and then I have my NOR. My NOR is M2, module 2, for example. The output of the input of it is Y, the other input of it is C, and the output of it is W, and then this ends my module. Okay, so I'm showing you 2 modules. One is I'm instantiating my own modules, and the other one is I'm using the primitives. Note the wire Y squeezed between my NAND and the module name. And then the same thing here, wire Y, because it goes between these two, I declare them there. All right. So what we have done is we have covered gates, we have covered numbers, we have covered transistors, we have covered how to wire transistors, how to wire gates, and let's go on to assign statements. Okay, I can have a module, how about overflow circuit, input A, B, S, these are single bit, output V, which is the overflow. This module, I can write an assign statement, a Boolean expression. Assign V equal tilde A, ended tilde B, ended S, sorry, ended S, ORed with A, ended with B, ended with tilde S. That's it. Okay. And I just put an assign statement here, and the assign statement is coming up with the output V, the overflow circuit, and let's say this is end module. Now, obviously, instead of the assign, I could put gates. For example, this is implemented as such: A, B, S bar, A bar, B bar, S, and then NAND it together again. Okay, but then in order to show the logic a little bit more clear, we use this symbol for the NAND. Okay, and this is overflow. Now, I have 2 input NANDs, I have 3 input NANDs, I can use primitives if I want, I can use my own NAND, but then my NAND is only a 2 input NAND, so I can develop a 3 input NAND if I want and then use it and so on. So there are options in doing this. Well, there's another option in doing this, and this is just do the overflow circuit all with transistors. Usually you don't want to do that because that gets a little bit too messy. All right, so I can put any Boolean expression I want. But then I can also use condition statement. Condition statement says this: module, a multiplexer that selects A, B, C, D, depending on select A, select B. Oh, why did I do this? Yeah, that's fine. Select C, select D, and puts it on the output. This is a decoded multiplexer. And then I can say assign output is if select A, then A, otherwise if select B, then B, otherwise if select C, then C, otherwise if select D, then D, otherwise none of the select inputs are 1, so put a 0. How do I put a 0? 1 tick B 0. End module. All right. If this was a 2-to-1 multiplexer like this one, A, B, select 0, 1, you would do, and then it was decoded, encoded. This one is decoded. Decoded means that every input has its own select. Encoded means that you have a binary number that selects. Okay. And if it is a 2-to-1 multiplexer with the binary select, S0 selects A, S1 selects B, and therefore you would say assign W equal, if select is 0, then A, otherwise B. Okay. All right. Assign Boolean and so on. Let me do vectors. Okay. So far, what I've shown you modules is module scalar, single bit. I can do module input 3:0 and 3:0 A comma B. Okay, I haven't decided what I want to build yet, but let's continue. We will build something. And then output 3:0. And then I'm going to give it another input function. Okay. I can use assign statements for this. Okay. What I want to do is this. If function is 0, I want to put the maximum of A or B on the output W. And if F is 1, I want to put complement of A on the output. Okay, so this is it. The way it works is if F is 0, then my output becomes max of AB, else my output is just A. Okay, so let's use we can use Boolean, we can use condition statements, and I'm going to be using condition statement here. I say that assign my 4-bit output is if F is 0, then then if A is greater than B, then if A is greater than B, then A, otherwise B, and then you put an otherwise for this first question mark, which means if F is 1, A goes on the output. Okay. If F is 0, this. If F is 1, this. So this is condition statement, and then I'm using vectors here. Okay, and module. When we're doing Boolean, I talked about Boolean expression, so you can put anything you want, and, or, XOR, and whatever you want, okay? And, but then, these are called bitwise, and therefore if I say, for example, let's do another one, assign y equal A and B, it means that y is 4 bits and A and B are each 4 bits, and then what happens is A, the 4-bit A, the 4-bit B, bit by bit A, B, bit by bit will be ANDed, these two, and come up with Y, these two, and so on. I could do XOR. Okay? I could do NOR. I could do OR. I could do whatever Boolean expression, Boolean operation I can have. So that's one thing. And then I can also use Boolean operations, but then in a reduction fashion. See, if I say, for example, module, let's call it I didn't give this module up here a name, so let's give it a name. Module, no name. Okay, no name. This module, let's call it reduction module. And my input is A. I have two outputs, Y and W. Y is OR reduction of A, and W is AND reduction of A. So I say assign Y equal AND reduction of A. Okay, that means take all the bits of A and then AND them together, come up with one bit. Assign, input 3:0 A. Output Y, W. I'm doing these examples on the spot. I just, whatever I can think of, I'm giving you. So there may be minor errors, but then the concept is probably correct. All right. Assign Y equal to AND of A, all bits of A, and assign, let's say, W is OR reduction of A. Okay. Or I could do something. Remember the parity circuit. I could say the third output. Let's give it another output. Y, W, V, for example. I can say assign V is XOR reduction of A, meaning that all bits of A XORed together. So V becomes 1. V is XOR reduction of A. V becomes 1 when the number of ones in A is odd. Assign, this one was W, is NOR reduction of A. Okay? Curly bracket. So you learned reduction, you learned Boolean expressions, you learned condition expression, and I'll show you adding in a few minutes. And then you have curly bracket. Curly bracket concatenates two things together. So what if I have B as another 4-bit vector? Okay, and what I want to do is I want to have A and B concatenated together and do the reduction on the concatenation of A and B. So this curly bracket, comma B, forms an 8-bit vector, and reduction is done over that 8-bit vector. Okay, same thing here. A comma B, curly bracket, and then W is done over the 8-bit A concatenated with B. So A becomes like, B becomes like this. This is B. And A becomes like this. And Y is this. Okay. If you want to put an end module. All right. Okay, let's do a few more things. Module, adder. Okay. Input, A, input, 3:0, A or B, output, 3:0, W, output, CO, carry out. And my adder is assign, that's again assign, W. Now, carry out becomes the fifth bit, and therefore I use curly bracket, carry out, comma, W. That gives me 5 bits altogether, and this is equal to A plus B plus. Do I have a carry in? No, I don't, so that's it. All right, and module. Or maybe I have module, full adder, input, A, B, carry in, output, carry out, and sum. We can write assign for the, this is Boolean, for the carry out is A ended with B, or with A ended with C, this is Boolean, or with A ended with B ended with C. And then I have assign sum equal A XOR B XOR C, and then we are done. The above is 4-bit, the below is 1-bit. Okay. I could build my 1-bit full adder by my 4-bit adder by putting 4 full adders together like this. Okay. A3, A0, B3, B0, and then carry these here. Okay. So let's do that. Instead of writing an adder all together, I say, let's do module, full adders, 4 of them. Again, the inputs are, as before, 3:0, A, comma B, output, 3:0, W, and output, carry out. These are full adder, each of them. And I'm doing a instantiation of all 4 full adders. Okay, the above full adder. So I do full adder. Okay, FA1, this one. Let me do something here. I have these intermediate signals that I have to name. I call them mid carries. Okay, wire. MC, those carries in between. And these are 4:, 0, 5 of them. And then this is MC 0. This is MC 1, 2, 3, and 4. Okay? So this is how I'm going to write my full adders. Full adder FA1. I write the instance name in lowercase, not to get mixed up with the module name. The inputs are, according to this, A, B, and carry in. That becomes A, I'm doing the right hand side, 0, B, 0. MC is the carry in, and MC is MC 0. What do I have for carry in? I don't have a carry in, and therefore I do an assign here that MC 0 is 1 tick B 0. Just to do regular structure, MC A0, B0, MC0, and then the next one, 1, 1, 1, and so on. And then the next port is the carry out, and therefore that would be MC. If this is 0, this is going to be 1, and then the next one is sum 0. See, that gave me my first full adder, the one on the right hand side. Then I have FA, FA 2, that takes A1, B1, MC1, MC2, and then S1. The last one, FA, I'm skipping 3, FA3, A3, no, the last one would be 4. FA3, I'm skipping. A3, B3, MC3, MC4, and then S3. Okay. Again, I didn't have a space for FA3. And then in module here, but there is one more thing to do. Okay, and that is MC4 really is the carry out. So I make another assign statement, put it anywhere you like. Assign carry out equal MC4. Okay. All right. We are covering a lot of things. Make sure you understand all of this, then you understand everything we have said so far. So I have an adder, and I have a an adder, and I have a well, I have added in two ways. This is obviously easier, but then if you want to do individual adders, and then you want to go inside the full adders and do the gates, and then inside the gates go do the transistors, this can become a much more accurate timing wise than the just single assign. All right, let's do always. Always is a procedural statement inside it, but on the outside it is a concurrent statement. I like to do a module, CMP, okay, input 3:0, A comma B, output greater than or equal. GE becomes 1 if A is greater than or equal to B. Okay. I can do it a million ways. I do always. The inputs are A and B, and therefore they participate here. The output is GE, but then I'm setting it inside an always, and therefore the output has to be reg GE. If A is equal to B. See, equal, you do equal, equal. Okay? Logical or we have the let's see, we have the comparison or the double or is for skip my memory right now. But anyway, if you want to say if A is equal to B, you do two equals. Or if A is greater than B, then GE equal 1 tick B0, else GE equal 1 tick B, and always and module. Okay? Let's say that I want to build an ALU that I want to build an ALU. Let's use a different color here. This is a nice one. Okay. I want to build an ALU. A, B, with a GE flag and a W flag. Okay. The ALU does two things. It creates GE and it creates yeah, and it creates the add of A and B. Okay. So what I want to do is I want to instantiate the compare and I want to instantiate the adder. So this is how I go about it. Module, my ALU, which does nothing. Very simple. Inputs are, let's not use A and B, let's use F and G. 3:0, F and G. Output 3:0, W. Output a single bit GE. I instantiate the comparator. CMP. I have to have a instance name. I call it comparator module. Comparator module. I connect F to it, G to it. Okay. And the GE, should I call this one GE flag? Okay, just to make it different. GE flag. So I connect F to the comparator. So what it is here is I have the comparator and I have the adder. Okay. Okay, I'm going to do a little bit better. GE flag. GE flag. Okay, I instantiated the module right above, and I'm also instantiating the adder. I call it adder module. Now, what are the ports for the adder? The order is A, B, and W, and the adder has carry out. I'm not using carry out. Okay, so I'm gonna do F connects to A, G connects to the second port, W connects to the third port, and then the fourth port is the carry out. I'm not using it, so I just leave empty. That means the carry out comes here, just let it go. Okay, leave it open. And that's it. That's the end module. So let me do the drawing here. What I have is this is a comparator. Takes these two, which is this, and the GE output of it connects to GEF, and then I have this, which is an adder. I instantiate that. And then just drop the carry out. This becomes my ALU, very simple or useless. Okay? Just showing how two modules can be instantiated. And also showing that I can write something in always, using always statement. That always statement could also be written as an assign statement, also as gate level or anything else. All right, so let's do test benches. Okay, and let's do this useless ALU and develop a test bench for that. Okay. I'm trying to get the color before I go to the next page. Right. Okay. I want to develop a test bench for this circuit. It has F and G, and then G, E, F, and W are the outputs. Okay, I develop this. Module. Useless ALU tester. Test bench. No inputs and outputs. Okay. And then you have inputs are A and B, and therefore I declare reg 3:0 A equal 4 tick B 0 0 1 0. I declare reg 3:0 B equal 4 tick decimal 15. Okay. I'm doing a test bench for this. I called it A and B. Fine. And then I have wire, something I want to connect to the GEF. I call that GE, for example. Something I want to connect to the ALU output, 3:0 W output, let's say. And then I instantiate my component. The component name is ALUVS. ALUVS. module under test. This is mandatory because this is my own module. If it were primitive, it wasn't mandatory. It would be optional. Yeah, see. Here FG come first and then W and then the last one, right? So A connects to F, B connects to G, and then is W output connects to the W, and then GE connects to the GEF of the module under test, which is that useless ALU. And so you have this declared, instantiated. Now you have to put something onto the inputs. Okay, I'm going to do this. Initial. I'm going to show you techniques different from what we have already seen. Okay, repeat 13 times. Each time, wait 13 times. That's a prime number. 13 is prime number. Each time, wait 13 nanoseconds, maybe more, because usually gate delays are within that range, so I want to be far more than that. So let's make it 31. Hopefully that's also, it is prime number. And each time A equal A plus 1. Increment A. And then end. That's one initial statement, only repeats something on A. Another initial statement. I don't have to put a begin. Repeat 20 times. And then this time wait shorter. Be something between let's say 23. And then this time B equal $random. That means put some random number on B. And then since this is only one statement, I don't need the begin and end. And also let's put something on GE this time, initial, and then begin, wait, there's no wait, sharp sign, 21, GE equal to no, I'm sorry, GE is the output, so I don't need anything else. That's it. The A and B are the only inputs, and then this is end module. Okay, we covered good amount of Verilog. Basically, everything we have talked about so far, we covered here. Fine, we are done. We have covered all of these, and then we did a review of Verilog. Thank you.